I apologize in advance because this presentation is going to be a little messy in the way that I've collected a number of things. Some of them, of course, as you probably know, my editor told me once, you only write one book. So whatever you say, it's always the same, it's just put in a different way. So, which is about what I'm going to do right now. So it's a combination of things that you've already heard, some of you, and thoughts that came to me during this session. So this is my first major conclusion. Actually, it's not a joke. You cannot imagine the number of intelligent things that cannot spread around because people take slides, print slides, try to distribute slides, and you just can't guess what the person that wrote the slides is talking about because you can't read. So it might be stupid, actually it's not. Now, here are some more minor conclusions. We have made here a number of calculations that are basically nil or everything. You know, they are very useful to frame the beginning of a conclusion. And of course, they are never of any use in real life because in real life, you never choose between paradise and hell. In real life, you make trade-offs given the possibilities that you have at hand at a given moment. Okay? So calculations that I love and rules of three that I love are basically helpful to make a first sorting in a way between what can eventually someday fly and what is doomed from the very beginning. That's the use of back-of-the-envelope calculations. Sorry, it's in the wrong order. My conclusion on what we call energy supply and fossil fuels is that basically we have a predicament, which is that we have to choose between a short and exciting life or a longer and more austere way of living. That's basically where we are. So either we want the party to go on as long as we can, and it's not going to be very long, or we choose deliberately to have less right now, and we will live longer. And I don't know whether it's happier or not happier, and the ultimate choice relies on society. It's not science, basically. You don't choose whether, it's not science that chooses whether you want to live less and a more exciting life or more and, in a way, restrict yourself. So what we can help to do, basically, when we gather in this kind of place is not helping people to take better decisions, because you don't know what a better decision is. You can help them to take more informed or better informed decisions. And I believe that we can have the tremendous ambition, because it's going to be a tremendous ambition, of helping the society to take better informed decisions. And a better informed decision is, as we say in French, ne pas prendre des vessies pour des lanternes. That is, not being mistaken in the result of what you are undertaking. That we can help. What is the terms of reference of this new science that we could dream of? That's what I'm going to show after. My belief is that we will have to invest in both mitigation and adaptation in a recessive world. This is brand new. We've never done that. We come out from a luxury world and a comfortable world, which is a world of growth. And in a world of growth, there are two things that you can do. You can test, mistake, and try again. When you're in a race against the clock, you cannot do this. And you can do both intelligent and stupid things at the same time, because the money that you invest in stupid things doesn't prevent you from still having money to invest into intelligent things. When you're in a recessive world, if you invest money into stupid things, you've lost twice. You didn't solve your problem, and you don't have your money anymore to invest into intelligent things. So basically, and that is going to connect to the ROI afterwards, you will see. Another thing that Michel shown is we are in a brand new world, again, regarding the way we manage money, because in a world of growth, you do not consider things the same thing regarding interest rates as in a world of no growth. I've already said twice, so I'm going to repeat it a third time. If we want to be heard, we have to have clients. That is, people that are interested in hearing what we have to say. There are two basic reasons in humanity for having an interest in something. One, it's because it's going to help you have a more pleasant time. B, it's because it helps you seduce other people. So basically, we must find something in these two basic things that pertain to human nature. The role of energy is absolutely crucial in the industrial societies, and I'm going to show afterwards that basically the way an industrial society evolves is primarily linked to its energy supply, and the rest is secondary issues. So I think that there is the urgent need for a kind of energy IPCC that is a place where we progressively agree on the scientific basis of what we are discussing, and we go up to the layer where people begin to disagree on what issue we are discussing. So let's take, for example, the climate. Everybody agrees on the fact that the atmosphere is composed of 21% of oxygen, basically 80% of nitrogen, and some minor other things. They all agree on that. And they say, whenever you want to mitigate climate change, if you make the assumption that the atmosphere is 50% oxygen, don't go any further, you are going to say nonsense. Okay? So I think that we should try to achieve some kind of equivalent. And for example, we could all agree on some things that I'm going to show just afterwards. We should therefore try the debate to be based on explicit and normalized notions. Explicit and normalized notions.
Normalized or normative is very different.
Either one, depending on what we're discussing.
Normative means value laden.
Well, normative. Normative. So basically, an egg, everybody knows what an egg is. Okay. I'm good. So it's normalized. Okay. So I'm going to show an example after for energy savings, for example. Actually, right now we are mixing three different things in energy savings, and of course they must be addressed in three different ways. We should try to provide methods to sort between what is physically feasible and what is not, which is of great use. Because if you say to someone it's physically impossible to jump from the Eiffel Tower and still be alive when you arrive at the bottom, it's of some use for people. We should try to achieve the design of methods that help to explicit counterparts that are not present in energy scenarios that you can find. It was already somewhere in the school that we organized 2 years ago. And that's also for great value. We discussed here a number of things, like, for example, explicit investment counterparts of transition paths that one suggests. We've discussed that a lot with renewables. We could try also to explicit net energy counterparts of transition paths, because actually what counts for society is not primary energy, but net energy. I'm going to discuss that after. And of course, EOI can also be of help for that. And I'm going to begin with one thing that I hope we should share from the very beginning, which is that whenever a political plan for the future tries to violate the first law of thermodynamics, you just discard it. What does the first law of thermodynamics tell us? It tells us that all that we can do regarding energy is take it from where it is, we cannot create it, and use it for our profit. So basically, what we do regarding energy is take some pre-existing energy in the environment and use it. Why is there pre-existing energy in the environment? Because nature was good enough to give it to us in the course of 14 billion years since the Big Bang, okay, for free. Because all, and that's a message to economists, all primary energies are free. The existence of the energy itself is free. It's a grant from nature. Okay, it's a gift from nature. So when you hear in the ecological world, wind and sun are free, this is true, but oil is free as well. Oil is free as well. Oil was formed, again, in the course of natural evolution, and it's free. Therefore, the cost of energy is only the counterpart, monetary counterpart, of labor and rents that you have to pay to other human beings, I insist, to other human beings, God doesn't have a cashier, to get the energy from the environment. And so you have a very simple conclusion from that, which is that the more an energy source is of poor quality, in physical terms, and the higher you will pay, because the more labor you will need to get the energy from the environment. So, and I'm going to show just afterwards that actually it's the main reason for which we went from renewables, because we were 100% renewables 2 centuries ago, to fossil fuels. I should bring this message to people like you, because as I said, what did the IPCC? The IPCC in the first place didn't talk to politicians who didn't give a damn. It talked to other people that had the time to take 2, 4, 10, 20 hours to understand the message. So actually, elected people are not interested into this. They're interested into making trade-offs between pressure groups. So you have to create pressure groups from this. And creating pressure groups from this is talking to people like you in the first place. I'm going to give you some simple example. So take this cube of air and this cube of air. Oh, sorry, I shouldn't have put that at the top. It should have appeared at the end. And assume that it's moving at 80 kilometers per hour. I'm sorry for American friends. You will convert that in miles per hour. It's about 50, I believe, miles per hour. Well, you know how to calculate the kinetic energy. That is going to give you the same amount of energy once gone through a wind turbine than 3 milliliters of oil. Picture the work which is necessary to do this compared to the work which is necessary to extract 3 milliliters of oil from the environment. And you get the economic consequence, which is this is unbuffered 8 cents per kilowatt hour, and this is buffered, because it's a stock, 0.3 cents per kilowatt hour. So what you have is basically a 50 to 100 ratio between the amount of work that you need to do this and the amount of work that you need to get this. And that 50 to 100 ratio, you will find it in the amount of work that you need to get a manufactured object, whatever it is, that did exist 100 years ago and still exists today. I'm going to show you this afterwards. So basically the real price of objects have decreased because of this. How, mass per square of the speed. Non, 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 non. C'est une énergie. Un demi de MV2. Un demi de MV2. And this is the reason why, in the course of history, we have done this. This is the consumption of renewable energy in the world, which is biomass. Then we've added coal. Notice that the coal use in the world never decreased since we began to use coal, and today 66% of coal is used to power, for power plants. Then on top of that, we've added oil. So there has been no oil-coal substitution. That doesn't exist. It's piling up. 50% of oil today is used to move things and people around, which is not at all the same function than producing electricity. Then, on top of that, we've added gas, then we've added hydro, then we've added nuclear, and then we've added what basically gets excited, get the press excited. And then I come to another conclusion. I've always been astonished by the fact that all scientists I know have got a very high ability to discuss their own field in which they work and take for granted what they read in the paper. Never, ever do this, okay? So never, ever do this. In the fields that you do not know, basically, the first you should listen to is people that work in the field, and never take anything that's written in the paper for granted. Never, ever do this. Never, ever do this. Never. Never. Another conclusion that I derive from what I've just shown is that all energies have specific uses, and therefore you cannot have sorry, I'm really sorry, it's in the wrong order again. Even among fossil fuels. So never in a model take fossil fuels at large. That's inappropriate. You cannot do this. You cannot do this. Fossil coal is not equivalent to oil. The oil is not equivalent to coal. You cannot say when I've got less oil, I'm going to use more coal. It is possible, but not at any cost, not at any conditions. And one example that I give is like, for example, if you want liquid fuels and you draw them from an oil field in the Middle East, it's going to cost you about $20,000 per barrel per day that you extract in investment. If you do the same thing with tar sands, it's going to cost you $150,000 to get a barrel per day. So if you reverse what I've just said, you have a given amount of money to invest into oil extraction. If you invest that amount of money into tar sands, the production that you will get per year is 5 times less than the production you will get from the Middle East. Okay? Which is basically the reverse of what Carrie King showed, which is that when you degrade the quality of energy, you have to increase the amount of people and the investment that you put into that energy, and therefore these people are not available to do something else. And so you globally degrade the amount of services that you provide to the society. And so one of the conclusions that you should not take for granted is the fact that if you go to renewable energies and that puts lots of jobs into the renewable sector, it's a good thing for society. It might be a good thing for jobs. But in the way, but there is one counterpart that you cannot avoid. I don't know whether it's good or bad, but one counterpart that you cannot avoid is that it's going to lower the amount of goods and services that you can get. That is unavoidable. Okay? You can say that it's good, but it goes with it.
That's correct if there is no unemployment.
No, it's not what I mean. If you go to the extreme where 100% people work in the energy sector, no one is left to take advantage of the energy you get. So you haven't got any goods and services. Okay? It's just what I mean. Actually, what we have seen during the course of this school is that the less people work in the energy sector, food included, and the more goods and services you have. Actually, it's a good proxy, the number of people. The fraction of the active population which is in the energy sector is a good proxy of the amount of goods and services that you will get. Which is counterintuitive, because when you advocate for renewable energies, generally you say it's going to create plenty of jobs, so it's a very good thing. Which is true, but it's not the only consequence. Now, why did we go from renewable energies to fossil fuels? This is a special. This is special for our foreign friends, because the French friends in the room, they know this by heart. This is something that you can do right out there, which is climbing on a mountain. The amount of energy that you invest, produce, whatever, when climbing up a mountain, so I took very easy calculations, 90 kilograms going up 2,000 meters, it's exactly 3.6 million joules. Sorry, 4,000 meters. So that's going to require about half a kilowatt hour of energy. So when you use your own body, your own legs, to climb up 2,000 meters, your legs will provide about half a kilowatt hour of mechanical energy. Actually, it's a little bit more than that, because what your center of gravity does is this, because you do steps. So it's probably closer to 1, but I mean, forget it. The order of magnitude is correct. If you do this 1 day out of 2, which is another way to say that you climb up from Chamonix to the top of the Mont Blanc every 4 days, at the end of the year, you will have provided 100 kilowatt hours of mechanical energy. So your legs, in the course of a year, can change the world, because energy is change, up to 100 kilowatt hours, basically. If you use your arms, and actually those of Mr. Arnold and not mine, and you shovel up 6 cubic meters of earth in the course of a day, same thing, E equals to mgh, you will come up with the conclusion that it's 10 times less energy that you will provide. And if you do this 1 day out of 2, it's 10 kilowatt hours per year. Well, it happens that 10 kilowatt hours is precisely the heat content of burning just 1 liter of oil. So basically, and of course you do not have 10 kilowatt hours of useful energy. If you go through an engine, you will get 2 to 4. But still, what this simple calculation shows is that in 1 liter of oil, you've got the same ability to change the world as in putting to hard work 10 to 100 people during a day. 1 liter of oil. Okay. You will see after how many liters we consume. If I convert this into its economic counterpart, suppose I pay this guy at the minimum wage in France. Well, my kilowatt hour will cost me a couple €100, or dollars, it's the same, to a couple thousand euros, whereas transforming the world with a machine will be available at the marginal price. I only count the cost of fuel. I will give you the slides. I mean, you can take a picture if you want, but at a marginal cost of a fraction of a euro. So in economical terms, going from manpower or man labor to machines allowed us to transform the environment for several hundred to several thousand times less than what we did in the past. This is why we went to fossil fuels. This is why we went to fossil fuels. We all became Superman, in the true sense of the word. We've got an exoskeleton which is tremendously more powerful than ours. This is why. Now I'm going to be very politically incorrect now. Assume we take a slave. Generally, a slave is not something you dream of when you're young. You know, when you ask people what they want to do when they are grown-ups, they generally don't say, I want to be a slave. So when you have a slave, you have to go and get the slave against his or her will, then keep him or her, prevent him or her from revolting, from escaping, etc., and you still have to feed him or her, otherwise you lose your set. Well, if you pile up all the costs that are associated to getting a slave and keeping your slave, you will realize that even having a slave costs you 10 to 100 times more than using a machine. And one of the reasons why slavery disappeared, in my own view, is not because we became good. I think that our genetic code is exactly and strictly identical to what it was 8 generations ago. I believe that it's just uneconomic to have slaves that revolt, that don't want to, that want to escape, that won't want, etc., and that have to sleep at night, when the machine that doesn't have all this inconvenience is 10 to 100 times more efficient. Which means, by the way, that when we are going the other way around, there is going to be a strong temptation of the rich to put back the poor in slavery. It's already happening, and it's going to be a growing temptation of the rich. If I look not at the energy supply of the world, but the energy supply per capita, this is how I can express it over the time in kilowatt hours per person and per year. And given the small calculation that I've just made before, today the world GDP would require, if we did not have machines, that humanity be 200 times bigger. That's basically the simple conclusion. So what drives the GDP today? Machines and energy, and not people. Which is why Germany is so well off today. It has the same amount of machines than 10 years ago, less population, so you have the same cake, and less people to share it. So basically, in present industrial times, what counts for the production is the number of machines. You need as many jobs as people to serve the machines, which is why when the energy supply is decreasing, you have less jobs, which is why. And you can keep the same amount of jobs only if you decrease the productivity of jobs. So basically, you need to decrease the productivity of jobs if you want to keep the same number of jobs in a world where the energy supply is decreasing, which is totally absurd for classical economists. But that's what you have to do. And when I say decrease the productivity of jobs, it means that if you decrease the number of work hours, you must decrease the wages in the same proportion. In the same proportion. So in France, the 35 hours could have been a very good idea if salaries had been multiplied by a ratio of 35 on 39. You also have the explanation here of the tremendous increase in the productivity of work until the oil shocks. And then notice that when the oil shocks happened, it corresponds to a physical event which is of tremendous importance, which is the stop of the increase at the same pace of the energy supply per capita in the world. And actually, in the OECD countries, it's not 0.4% per year after the oil shocks, it's 0.0% per year in rough figures. So what Charles showed with a very nice drawing the other day, I summarize it this way. Super Mario, of course, is Super Mario Draghi. This is the way we figure our productive system. And of course, the correct representation is this one. We have resources that we transform and that we get production, and capital is part of the production that we have made that we reuse for future production. Basically, it's something that doesn't destroy itself when we use it. Like this building is not going to destroy itself, or hopefully, while we're in. And in the course of transforming resources, our muscles account for 1, and machines and energy account for 200, which is why the primary driver of GDP is the energy supply, because it drives the amount of machines that can work and that can transform, and the economic counterpart of that transformation is GDP.
That 200 is for the world population?
Yeah.
So like Americans actually...
OECD country, France is about 500 to 600, and I would guess that American is about 1,000. If you have a bottleneck on the energy supply, no matter how many liberalization of the markets and whatever, blah, 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 you will have less GDP. And I don't have the time to present them today, but I've done this fact-checking for any OECD country that you can think of, and it works everywhere. Everywhere. I'm going to show you the case of Spain just after. If you have less resources, like, for example, less fish to fish, you have less GDP for fishing, or less production. This explains this. When I did this the first time, I was very surprised to find this result. Actually, it's deflated GDP in constant $1 billion for the world. I can do this for any country for which I have the data. And the energy consumption, I'm going to suggest another word for consumption in a couple minutes. From 65 to 2014. And what you can see is a joke that I've already made, which is that the best macroeconomic model in the world is a straight line. This is the case of Spain. But we have other European countries like this. So what happens to Spain? Same thing. They have more energy, they have more GDP, and then, you see, turnaround. And the turnaround looks like this. What does it mean? What does it mean? Sorry. It means that the chronological order of this is that first you have less energy and then you have less GDP. If you look at the financial crisis of Thailand, for example, in 1997, it goes like this. First you have an economic problem, and therefore people have less money, and as energy is also a commodity, they use less. But regarding Spain, the reason for this is very simple. Oil accounted for 50% of the primary energy in Spain before what is so-called the crisis. And we are in a constrained decrease of the oil supply in Europe since 2006. And so the energy input in Spain decreased. And so the GDP of Spain decreased. And I could show you this curve for Portugal. It's exactly the same for exactly the same reason. This curve for Greece, it's exactly the same for exactly the same reason. And this curve for Ireland, it's exactly the same for exactly the same reason. So, I suggest that we also agree on this. We do not have GDP that calls for energy. We have a gift from nature, which is energy, and therefore we can transform and have GDP. And actually, Zeynep has shown, has performed the work with Gael, which is confirmation with causal tests that I never understood anything about, but I trust her, that says that it's the correct way. But I mean, it's very simple to understand. Again, GDP is piling up added values, and added values is is a transformation. So when you pile up added values, you have to pile up the counterpart, the physical counterpart of a transformation, which is energy. No energy, no GDP. As simple as this. So,
which you could summarize summarize by saying that it's just a change of units.
And
That's why it's a straight line.
So I suggest that we never talk of energy demand, that we talk of energy availability. Okay? Energy demand is energy availability, or rather is capped by energy availability. You cannot ask for something that doesn't exist. Well, you can, but I mean you won't get it. You have no link between the price of energy and the world GDP. This is actually the main driver for the price of energy in the world is the price of oil. When you look at the trade, the energy trade in the world, it's basically oil that occupies what 70 or 80% of all of it. And here I've done a very simple plotting. Here is the constant price per barrel from 1960 to 2014, sorry. And this is the constant, this is the world GDP in constant dollars. If the GDP should decrease when the oil price increases and vice versa, the dots should be aligned along this kind of pattern. Okay? Cost more, less GDP, cost less, more GDP. And you can see on this graph that there is absolutely no such link. You can have the GDP increasing with a decreasing price of oil, then with an increasing price of oil, then with a decreasing price of oil, then with an increasing price of oil, then etc. There is absolutely no link between GDP and the price of oil, so forget the price. There is absolutely no link between the price of oil in nominal dollars and the volume of oil. You have plenty of models in which you have an elasticity between price and volume. It's just a false assumption. It doesn't work because it doesn't work. Here, same thing. You have the amount of oil which is consumed in the world. Before you had something like this. Before 1921 and today. And here you have the price per barrel. Same thing. If we should consume less when the price is more expensive and vice versa, the dots should be aligned along this kind of pattern, which is not the case. Actually, you have two stable regimes. One which is the volume does anything with a constant price, then the price does anything with a constant volume, and then you play the same game again. So there is no elasticity. You do have one, actually, but it's not between volume and nominal prices. It's between volumes and real prices. What is a real price? It's the price of something divided by what you earn. So, by what you earn. So this is the nominal price of the barrel. This is what you earn, for example, in the US. And if you divide this by this, then you get the true elasticity. So basically, the true elasticity is not between the price and the volume, the price in nominal dollars. It's between the real price, which is the amount of time that you have to devote to buying something, and the GDP. What you can see here is that the real price of a unit of energy has been divided by 15 in the course of a century. And if you think exergy, because the efficiency of that energy use has been greatly improved, then you get that 50 to 100 ratio, which is the same that if you think of the time you have to devote to buying a house today, for example, is basically 50 to 100 times less than what it was a couple of centuries ago. That's just what I mentioned before. That's the energy supply per capita in the OECD countries. So this is the party, this is less party, and this is the beginning of the hangover. And the hangover will go on. If you look at the second derivative of the energy supply, that is the variation of the variation, it's been negative for 50 years. Could comment on why it is so. It's what I call the predicament of the Easter eggs regarding gas, oil, and coal. I can explain. And this is the evolution of the growth rate of the OECD members. You see, it follows exactly the same pattern. And my personal bet is that it's going to follow this and not come back to the average value over the last 50 years. So we will have to transition in a recessive world. This is two very simple extrapolations that I've made for the primary energy supply of the OECD zone. This, I prolongate the arithmetic average growth over the last 50 years. And there, I prolongate the second derivative. And you see that the result is not exactly the same. Now I'm going to discuss something else, which is the notion of saving energy. So obviously, all you've seen during this week is that we should save energy, etc. What energy should we save? That's a good question. As you probably know, when we talk about energy, there are three energies that we can distinguish. So the energy that we extract from the environment is called primary energy. We never use primary energy because you don't power a plane with crude oil and you never take the gas directly from the gas field to your kitchen for cooking. In between, you have what is called an energy system. We transform primary energy into final energy, and because of the first law of thermodynamics, you have losses in between. Because, no, actually, you cannot have more here than here.
That's the first law, but the second law is...
No, the second law is on the quality, but the first law is that you cannot have more here than here. And then that energy, you are going to use it for something that is of interest for you. Motion, heat, whatever. Elected people love this. They love the idea of improving this efficiency because that calls on a restricted population of voters, which is engineers. So this doesn't require that you get up from your seats and sweat a lot. It doesn't require it, okay? Engineers, these people that are overpaid and they just have to work harder so that we get more efficient batteries, more efficient power plants, more efficient cars, more whatever. This, it's unclear because when it's this, it is still an engineer, but sometimes you can also buy a small fridge and then it's not the engineer's problem. So I derive from this very simple diagram the idea that we can distinguish savings into three categories, and that's also something I hope we should agree on. If I use the same service, but engineers have been so clever that it requires less energy, then it's efficiency in the true sense of the word. So I still have the same car, drive the same mileage, etc., but I consume less fuel. That's efficiency. So this is example. So it doesn't hurt the final consumption. So the end consumer is happy and can vote accordingly. Something else which saves energy, I call it sobriety. Sobriety is I deliberately decrease the quality or the amount of services. So I buy a smaller car, and therefore I can't take grandma and the dog when I leave for holidays. Okay, send them by train. Or I don't go on holidays, or whatever. I live in a smaller housing space. I buy less beauty cream, whatever. And that's sobriety. And I can have the same thing, but I never ask for it, and that's poverty. So the difference between sobriety and poverty is not in the fact that I reduce the number of goods and services that I use. It's in the fact that in one case I desire it, and in another case I never ask for it. And that's the distinction I would like to submit, because in this case you bother the engineers and you let everybody else quiet. In this case you make degrowth desirable, and in this case you manage degrowth that people never ask for. So it is three very different things, and I think that in scenarios, that's where I wanted to come, we should make explicit what fraction comes from this, what fraction comes from this, and what fraction comes from this, because that has major societal implications. I think I've got not that many. Now, ROI in this thing, as it is, what turns to be a good proxy for a number of things that are relevant in thinking all this transition, which is capital cost. We have seen that the lower the ROI is, the higher the capital cost to get a given unit of final energy. It's my final slide, or almost. It is a good proxy for what level of sophisticated services the society or the system will be able to provide to a society. So it's something which can be of great value not to make the best choice, because as I said, the best choice is a moral choice, but to inform those who are part of the decision-making process, which in a democracy involves everyone, because you vote whatever you know. We have, in my view, to try to be precise on what we are really talking of. So I'm going to give you my interpretation of ROI. So we have the grant of nature, or the gift of nature, which is here. Again, I repeat it, everything is free. 14 billion of euros since the Big Bang, all is free. The table of Mendeleev was created in the first generation of stars, free. Climate system came on Earth, free. We have an ocean, free. We have the genetic code of 30 million species, free. We have, and snow in the winter, in les Houches, free. All this is free. All this is free, okay? And in economic models, you never have the externality of losing something which is free. Never, ever. Never, ever. You don't have that. So that's also a major bias, which can be corrected if you think about it, but presently it's a major bias. Part of this primary energy and resources is used to design the energy system itself. Then the rest can go through the energy system and provide final energy and, of course, losses. Part of this final energy has to go back to the energy system because it is required by the energy system. And so the rest can go through other machines and provide services and losses. My suggestion for calculating an ROE is close to an LCA approach, because if we want to give something which is useful for political decision, I think that the major world is what you depend on, what you rely on. So what is necessary in a physical way for the system to exist. And for example, in what I've just shown, it is necessary for the energetic system to exist that you have this part that goes in, this part that goes in. So you could take, for example, the ratio of the final energy that goes there on the primary energy. That would be, in my view, a good definition. But you could also take the part that goes there on the part that goes there. And that can be, I would say, a layer of discussion when there is room for agreement or disagreement, because it all depends on what you want to do with the information. Where is the client? Okay? But you must start from what nature gave us. So what Fabien explained on batteries, it can be an add-on, and it's a useful add-on. But you have to begin from this. You cannot talk of the ROI of a battery. Makes no sense. Okay? So you have to start from what nature gives us, and nature gives us existing energy, because otherwise we do not have energy because of the first law of thermodynamics. And I will finish with 3 slides that you've already seen from Jean-Pascal, but I will give additional information on them. So as Jean-Pascal said, this is there are 2 major straight lines to have in mind when you discuss the energy-climate predicament. The first one is the straight line between energy and GDP. The second straight line is this one. It's between cumulated emissions and the average temperature increase that you will get in 2100. Let me recall that the average temperature increase is not something abstract. It's a proxy for the amount of disorder that you will get into the environment. Okay? It's a proxy for the amount of disorder. Don't think that it's going to remain external to human economies forever. Actually, it's not. If I had time, I could explain to you why the turmoil that we have had in the Mediterranean basin since 2011 is closely associated to an energy and climate issue. It's not, of course, the sole factor, but there is a direct link between the two. So it's already there, the energy and climate problem. We don't have to wait. We do not have to wait until 2100. As of today, we have emitted, that Jean-Pascal showed in another graph. I put the 2 information on the same one. 2,000 billion tons of CO2 equivalent in the atmosphere, and we have already signed for something between 0.8 and, if we are not lucky, 1.7 degree of temperature increase. Okay, if I take the mean value, it's 1 point something, so That's one of the things that allows to say that the 1.5 in the international talks is something which is of no practical value. It can have a psychological value, so as such might be useful to keep it somewhere, but it has absolutely no practical value. If we want to get to the 2 degree, yes, we have to stick to no more than 3,000. This is where the 2,000 come from. So what are we going to suppress if we want to stick to the budget? This is the proven resources of coal, oil, and gas converted into CO2 emissions. So if we drill, extract from the ground the proven reserves of oil, gas, or coal by energy and by region, this is what we get. So for example, if US basically extracts and burns all the coal it has, that makes 500 billion tons of CO2, which is half the world budget that we have until 2100. If we use all the oil that we have, it's about 700. So we can use all the oil we have, but from tomorrow, we do not use anything else. Okay, so tomorrow, whoever in this room uses a single gram of coal or a single cubic meter of gas, you stop. Okay.
What about capture?
Pardon?
No time, no time.
I will answer that later. Actually, it comes back to what I said before. You have to explicit the counterpart of spreading CO2 capture and storage. So the investment, the time lag, the transaction cost, etc. And you realize that it's not going to be a game changer for the 50 years to come. Now, any macroeconomic model that takes a representative agent assumes that you can mix up this, and this, and this. Of course, it's not possible. I mean, you are going to have a dogfight between nations regarding who is going to use what. So, obviously. And I'm going to finish with this. This is the pie chart of the emissions in the world. 20% today come from coal power plants. Obviously, it's one of the things which is easy to suppress if we go nuclear. It's not possible to suppress it if we choose solar panels and windmills. Because the capital costs associated to the second option are way over in a world of decreasing productivity what we will be able to find to suppress them. So one of the things that I advocate is that saying that anyone who is in favor of windmills and solar panels actually is in the favor of keeping coal as long as possible, and therefore making climate change as high as possible, which is totally counterintuitive, because in the public debate, you will hear exactly the opposite. I'm in favor of the environment, so I'm for solar panels. I say no. If you're for solar panels, you're for a big mess. Precisely because it's a waste of time and capital to solve a small part when you could solve a bigger part. You have also oil and gas power plants. 5% comes from cement. How do we build in a world where we have to divide emissions by 3? 10% comes from the industry, and among this 10%, about 5% also comes from steel. Again, boilers in buildings is about 6%. Transportation is in 4 parts that are not equivalent but are close. Keep in mind that the world emissions, the emissions coming from the cement industries in the world is about equivalent to the emissions coming from the trucks. Eating is a big chunk, and deforestation, which is an upstream process of eating, represents 8%, and you have others. So when you look at this, the practical question is, how do we divide emissions by 3? Where do we start? What do we do? And again, having normalized notions to discuss and try to explicit the counterparts of action is, in my view, absolutely crucial. Well, I had other things to show, but I do not have the time, and I will suggest, I will end by what I've said. What we have to invent is the scientific basis of a discussion in the society. But I said the scientific basis of a discussion in society on what energy is exactly and how we can bring and separate this issue into what we should all agree on, like the carbon has 6 protons and it's like this, and things that are open for discussion, but on the basis of what we all agree on. And today we basically have a big mess in the public debate on energy, and I think that if we can create the something that helps to clarify this debate, we would have done something very useful for myself, I'm young enough, and the people to follow for sure.